Hello, everyone, and welcome back. So this is the final review for our class, and we are going to go over some of the important concepts that I have tried to introduce you in this class. And this will also help you to prepare for the final exam. So let's get started. So if you recall, the overall idea here is to actually use matrix methods to solve like a given problem in structural analysis. There are many other methods that we could have used, but it turns out for like all the modern programming like is done using stiffness method, and that is like the basic method that is used in all the softwares that you are going to use in the industry also. And so it's a very modular method. So we can see that we use the same ideas, and we were able to solve different kind of problems. And so in our class, actually, I have introduced different elements. So when I say elements, it means that these are like mathematical representation of some physical structure. So for example, I have introduced 1D bar or spring elements, and we also talked about 2D truss element, 3D truss element, the beam elements, 2D frame elements. And then finally, actually, what we did is we tried to put all of these things together into a programming language using MATLAB. And I hope that you were able to see that how can we solve even like big problems using a stiffness method in a very modular way. And that is the benefit of this method. And this is, you can think this is a very introductory course. So this is like a first course in matrix method. And there are many advanced versions of this course. And if you ever go to a graduate school, I'm pretty sure that you will learn more about these methods. But I think this class is able to give you some basic understanding of matrix methods for structural analysis that are the backbone of any kind of modern software of that is used in the industry, or like any other software that is used for structural analysis is based on actually stiffness method. So what I want to do today is I would like to go over the basic ideas and what we have covered in the class, and the focus is primarily to give you some background, like to give you background means in terms of like what is necessary to do good in the final exam. So I want you to understand the basic concepts, and hopefully that will help you to prepare for the final exams. And the final exam is going to be comprehensive, so you want to make sure that you understand all the concepts in a very careful way. So this is the overall strategy of the stiffness method, and I'm pretty sure by now everyone is familiar with the strategy. So in the first step is whenever you have a given structure, you try to discretize the structure and identify the nodes and label the corresponding degrees of freedom. So this is always the first step. And in this step, actually, you have to make the decision how you want to discretize the structure. For example, for the same structure, you can put more number of elements to solve the system. But in this case, that means that in this case, you will have more degrees of freedom. So it's a designer choice, or it's like if you are a structural analyst, so that's your choice, okay? How do you want to discretize the structure? And the second step is determining the element stiffness matrices. So once we discretize the structure, so we have discretized the structure into small pieces that we call sometimes finite elements. And then we need the element stiffness matrices for all of those elements. And also the load vector, or POE vector. This in our class, we call this as fixed end forces. And this comes because of temperature, fabrication, or whatever the loads that are acting within the member, okay? And finally, we assemble KE and POE for every element into a global system that will give us a global stiffness matrix for the entire structure and the global load vector for the entire structure. So this PO is the effect of all the forces that are applied within the member, okay? So there are two types of forces we will see. One is directly applied at the nodal points, and the forces that are applied within the member. So PO is the effect of the forces that are applied within the member, not on the nodal, or not at the nodal points. And finally, we apply the boundary conditions after assembling K and PO. And in this case, boundary conditions means we want to describe what are the displacement degree of freedom that are known, and what are the loads that are given to us. In this case, you have to specify what are the loads at the nodal points. Okay, so this is where you apply the boundary conditions. And after applying the boundary conditions, we can solve the resulting system. And after solving the system, we go back and we can find the support reactions, and then find the element forces, what if needed. So if for a class, this will be like problem dependent. If the problem is asking you to find the element forces, you can go ahead and find the element forces, and so on and so forth. So these are the basic steps in analysis. And practically, it turns out that no matter what kind of structure it is, these are the steps that are needed. And so we have to do these steps in this logical fashion. So we already looked into what is the global system looks like. So global system looks like this. So we have a P is equal to KU plus P0. So P is all the nodal loads. So you can distinguish between two types of nodal loads. So if the displacement degrees of freedom is unknown, then the corresponding load is actually a nodal load. If the displacement degree of freedom is actually given, then the corresponding load is a support reaction. So P can be here split into two parts. And here U is the global displacement vector, and K is the global stiffness matrix. And P0 is the contribution of the loads that is coming from like the forces that are acting within the member. So this is how we built up the system, and then we can solve the system. So when we are solving the system, some important things that you have to remember is that K is a singular matrix, because when we are looking at the entire global stiffness matrix, this is always singular. Okay, so we never invert the entire stiffness matrix of the system. We invert only the KFF part, but we'll go back go to that point in the next slide. So important thing to remember is K is a singular matrix, so determinant of K is always 0. And the other important thing you want to remember is K is a symmetric matrix. So if it's a symmetric matrix, actually it turns out that you don't have to really like calculate all the K. You can just calculate upper half or lower half of the K, and then you can use the same entries in the rest of the matrix. So K is a symmetric matrix, and symmetry actually comes from the inherent property of the structure. We didn't talk about the theoretical basis of symmetry, but for now you can assume that almost all the structures you're going to see in practice, they will have symmetric matrix. There are some very special cases you will encounter matrices that are not symmetric, but the idea will remain the same. Idea is the solution techniques, and nothing is going to change. We still can solve the same the problems even with non-symmetric matrix in the same way. Anyways, once we build the system, building the system means you have to figure out what is the K, what is the P0, and what is the given nodal loads, and then we can solve the system. And we always try to solve the system by partitioning it. So partitioning means that we can split the U into free degrees of freedom and the supported degrees of freedom, where the subscript F means it's a free degree of freedom, S means it's a supported degree of freedom. And similarly, we can partition P also in PF and PS. So PF is given to us, PS is the support reaction. So PS is not known, because PS corresponds to US, and US is given. So US is given, so PS is not known. And PF is given, this means that UF is not known, so UF is an unknown. PO is given, so both POF and POS, this is all given, so this is all known. This is a contribution of member forces that comes from fixed end reactions. And then finally, we can take K and like partition it into 4 parts, like KFF, KFS, KSF, and KSS. And we can solve this system in a partition form like this. And so we wrote the first equation as PF is equal to KFF UF plus KFS US plus POF. This is just the first equation here in the block form. And this is the second equation here in the block form. This is PS is equal to KSF UF plus KSS US plus POS. And what we do is we solve the first equation for UF and then back substitute UF in the second equation to find PS. So it's a two-step process. So first we solve for unknown displacements and then we solve for unknown support reactions. This is always the case, okay? So the solution strategy always looks like this. But there are some important points you have to you can remember to make the solution process a little easier, especially when you're solving these problems by hand. For example, sometimes US is 0. So if US is 0, it means that all the supported displacements are at 0. Then you don't need KFS and you don't need KSS because this gets multiplied by 0. Okay, so this is an important observation. And if only some values in US are non-zero, then you can just assemble the only like particular degrees of freedom in KFS. So you don't have to assemble the entire KFS, only the columns corresponding to the degrees of freedom that are non-zero. So we have discussed about these issues earlier. So I'm pretty sure that everyone understand how to do this algebra in a simplified way. And with this, we can go ahead and solve the system. Again, the one important thing is because this matrix is symmetric, so KSF is actually KFS. So you never have to calculate it twice because if you calculate KFS, you already know what is KSF, or if you calculate KSF, you know what is KFS. So just remember the symmetric property. It's important. Similarly, KFF is also symmetric. So you can remember some symmetric properties and make use of the symmetry when we are solving. And again, I'm just saying here, if US is equal to 0, then we don't need KFS or KSS. So just some important points you have to remember. You should remember or to just simplify the solution process. In this, and now we want to go over like individual element and let's see like what are the things that we have learned. One important thing before I move forward is I want to again discuss about the stability of the system. And we said that stability is related to the eigenvalues of KFF. And actually, stability tells us whether the given system is stable in the sense that it can support the loads, or it's not stable means that it cannot support the loads, whatever the loads you're trying to apply on it. And stability is related to the eigenvalues of the system. And if all the eigenvalues are greater than 0, then we say that the system is stable. And system will be stable if you have correct boundary conditions. For example, if we have supported the structure in the correct way, okay? And if you have enough number of members in the structure and you have done these exercises. So there are two issues that can create instability in a structure. So you can always go back and check your boundary conditions if your structure is supported carefully and correctly, and if you have enough number of elements within the structure. And typically this can be an issue if you have a large, like a 3-dimensional structure. It's not very easy to visually see why there is a instability in the structure. But if you do the eigenvalue analysis, you can easily detect the instability, and you can actually detect what are the unstable modes. And looking at those modes will tell you, okay, this is the reason the structure is unstable, and you can go back and fix the issues. And as I'm saying, the issue is mostly related to the boundary conditions or the lack of members. Sometimes you can make a mistake. For example, you put an E value to be 0, and then you will have this issue of eigenvalue is equal to 0. But most of the modern softwares, actually, they will not let you put like some incorrect numbers. They will like give you a warning that you're putting some wrong number for a given property. So hopefully those kind of mistakes are not there. And then you can always like take your KFF and check the eigenvalues. And I think if you check any kind of modern software, they should be able to give you the eigenvalue of KFF matrix, just to see whether the system is stable or not. Okay, but this is the overall idea of the stability of a structural system. I also want to point out here is here we are only discussing stability of a linear system. Stability, it turns out, is a very deep concept, and it can be studied. It can be studied in various ways. For example, we can discuss stability of a nonlinear system also, and then the idea of stability is a little bit different than what I have presented here. But overall idea is the same. So as long as we have a structure that is able to like carry on some loads in a reasonable way, we'll call that system as stable. If it's not able to carry the loads, then we are going to call that system as unstable. So I hope that you can actually remember this idea of stability and use it whenever is needed. So let's go over one by one over all the elements that we have covered in our class. So the simplest element that we have covered in the class were like a spring element and a bar element. So spring and bar element are very similar. On the right side, we said it's I node, and the J node is on the left side, and there are 2 degrees of freedom, Ui and Uj. So both bar and spring elements are similar. They have 2 degrees of freedom, Ui and Uj, and the forces at the I node is Fi, and the force at the J node is Fj. And they are related to the Fi and Fj. These are the nodal forces. They are related to nodal displacements by this 2x2 stiffness matrix. And we derived that stiffness matrix using simple ideas. And here K is the stiffness of the spring. So this is like a physical property of the spring. And similarly, for the bar element, the stiffness matrix we derived was Ea by L times this 2x2 stiffness matrix of 1 and -1. And you can see that the stiffness matrix of spring and bar element is very similar. So if you change, if you take K is equal to Ea by L, the spring member becomes a bar member. So mathematically speaking, spring and bar member are like the same. Depends on the how do you think about the K. Again, for the bar members, when we derive that coefficient Ea by L, we assume that the area of the member is not changing. And so area is uniform across the length. Also, E is not changing. So E is the modulus of elasticity. So we assume that E is also not changing along the length of the member. And here L is the length of the member. So you can see that the stiffness of the bar member, you can think stiffness coefficient as Ea by L. So this is the stiffness coefficient for a bar member, and it's like so this is for a bar member with a uniform area. And then what we did is we also derived stiffness for a bar member with a non-uniform area. In this case, what happened, we said that, okay, the area is changing uniformly from one end to another end. So area at node I was Ai, and the area at node J was Aj. And it's linearly varying across the cross-section. And we derived that expression of K. So K was like, it is the same form, but the stiffness coefficient K was E divided by L, Aj minus Ai divided by log of Aj divided by Ai. So this was the stiffness coefficient we derived, okay? Here, Ai is the area of node I, and Aj is the area of node J. And so if you have a non-uniform bar member, make sure that you use this, this stiffness matrix. And similarly, the force and displacements are related using the stiffness matrix, and actually it has the same form. Even only the K value is changing. So K is here, is this coefficient here. So you can compare this this stiffness matrix for compared with the spring element or the bar element. So overall form of the stiffness matrix is the same. Only the coefficient is changing, okay? So this is something you should try to remember. This is the basic idea of the stiffness for bar or spring members. They're very similar. And I hope that you are able to use these things correctly. And next, what we have also considered it for a uniform bar members, we considered some fixed end forces. And if we consider fixed end forces due to uniform traction, temperature change, and fabrication error. And these were the numbers that we derived. So, and in this case, when there was a temperature change, we said that, okay, delta T is positive if the temperature is increasing above the ambient, and delta T is negative if temperature is dropping below the ambient. And the ambient temperature is the temperature at which the structure was actually fabricated. And the fabrication error, actually, the sign convention here we used was delta L is positive if the member was created too long, and delta L was negative if the member was created too short. And we derived these fixed end forces for different cases. And then what we can do is, if you want to calculate the member forces due to all the effects, we can use the idea of superposition. So this is the force Fi and Fj due to all the effects. So using superposition, the fourth is the force due to displacements. This is just stiffness matrix times the displacement vector plus force due to traction plus force due to temperature plus force due to fabrication error. And this is how we can actually consider all kind of different like sources of loads in a bar member. And the same strategy is actually used for even trusses and frames and beams and so on and so forth. So this idea is used everywhere, okay? And here, so we are going to, in our class, actually, we only consider temperature and fabrication for the bar members. But actually, it turns out that we can also use the temperature and fabrication for the beam members also. But we have not considered it just because we didn't get enough time to move to that topic. But the idea, you can think about, the idea is the same. So if you have a temperature effect in a beam member, it can be considered exactly in the same way, okay? And after the bar members, we consider 2D truss elements. And we derive the stiffness, this 4x4 stiffness matrix for the 2D truss element. And actually, in this case, the degree of freedom were defined in the, so you can think that a truss member can be oriented in any direction in two-dimensional space. So orientation was defined in terms of angle theta. And it was that angle theta was measured from the global x-axis and moving anti-clockwise. So we talked about how to measure this angle theta here. So make sure to review your notes on how to measure the angle theta. And the truss member has 4 degrees of freedom. So the degrees of freedom are always ordered as Ui, Vi, Uj, Vj. So this is the ordering of degrees of freedom. And then the corresponding forces are Pxi, Pyi, Pxj, Pyj. And this is the 4x4 stiffness matrix that we derived. And important thing to remember here is that actually, if you see, the structure of stiffness matrix is very simple, because once you know these 4 entries, the other 4, like the rest of the entries are like either the same entries or multiplied by a negative sign. So you just have to really calculate C square, S square, Cs, and then rest of the entries are repetitive. And make sure that you multiply it by AE by L, the stiffness coefficient here. And we also considered temperature and fabrication error into 2D truss elements. And this is the temperature and fabrication error force vectors. Like this is the fixed end forces that we have to add if the temperature or fabrication is present. And make sure that you follow the right sign convention. So delta T is greater than 0 if the temperature is increasing above the ambient, and less than 0 if the temperature decreases above ambient. Oh, sorry, it should be decreased below. So there's a typo here. I'll fix it. And delta L is greater than 0 if there's a fabrication error of too long, and is less than 0 if fabrication error is too short. So just make sure that you remember the sign convention. And finally, if you look at the equilibrium of one truss element, so we can use again the principle of superposition and find the all total forces in a truss is actually the stiffness matrix times the displacement. So this first term is the contribution of displacement. Second term is the contribution of fabrication error, and the third term is the contribution of temperature effects. So this is the total force in the truss member. But we said that, okay, instead of representing like these 4 numbers for trust member, it's better to just calculate the fourth member using just one number, and that is and we calculated this number. We can we derived this formula, and we said that, okay, the force in the trust member should be calculated like this. So we can calculate just one number. It will be either tension or compression. So if we can calculate F, and if F is greater than 0, then it means it's a tension, or if it's less than 0, it means it's compression. So, and F has a contribution from displacements, fabrication error, and the temperature. So F contains everything. So this is the way to calculate member forces for a truss element. And again, here the idea of superposition is used to get this answer. Next, we considered the beam element. And in the beam element, actually, we considered different cases. In the first case, we considered beam elements with 4 degrees of freedom. So we consider this is the I node, this is the J node. For the beam element, the right node is always the I node, and the left node is always the J node. Sorry, the left node is always the I node, and the right node is always the J node. And this is always the configuration we'll consider for the beam element. And the degrees of freedom are ordered as VI, theta I, VJ, theta J. So there are 4 degrees of freedom. And this is the stiffness matrix we derived. We derived the stiffness matrix by solving the differential equation of the system. And this gives us the 4 forces, Pyi, Mi, Pyj, Mj. And these are the positive directions of these forces and displacements. So this is the stiffness matrix that you should use if there are no axial effects on the beam. So it means that if you have a structure like a beam structure in which there is no axial forces acting or axial traction acting, then you can ignore the axial degrees of freedom, and you can use this 4x4 stiffness matrix for the beam. So it depends on the problem. So if the problem has axial effects, then you have to use a 6x6 stiffness matrix for the beam that we will talk in a moment. So we have done a lot of problems in which there was no axial forces acting on a beam, only the flexural effects were there. So whenever there is only flexural effects, we can just use a 4x4 stiffness matrix for the beam, for that beam element. In this case, for the beam element, we have considered many different kind of loading that comes from the member forces. So we considered, for example, uniformly distributed load and point load at the center. So you can see that these are the fixed end forces due to these kind of force distributions. The important thing here is I'm not writing any axial forces. The reason is the axial forces are 0. So there's axial force here, but that is 0. There is axial force here, but that is 0. So I'm not showing any axial forces in these configurations because they're all 0 here. And similarly, these are some other load cases that I have shown you earlier also in the slides. And actually, I have also given you more load cases with all those fixed end forces. So these are all already given to us, so we can just use these values. And if you think about how we actually get these numbers, these are actually derived by solving the differential equation of the beam. So we can take the differential equation of the beam and put given a loading and just solve that differential equation. But people have already done this exercise, and now they have tabulated all these numbers. So we are just using these numbers directly. And whatever is the fixed end forces that is needed for a given problem, I will provide you for the exam. So you don't have to remember these numbers, but as long as you know that they are there and how to use them, that is what you want to remember. Finally, this is a superposition for a beam element with 4 degrees of freedom. So you can see that if you want to calculate the total force is the force due to the displacements, that is the stiffness matrix time displacements plus the fixed end forces. Okay, and in this case, because there is no axial effect, I'm not considering the axial degrees of freedom. So this is just a 4x1 vector for the beam element. Again, now you have to be careful when you're doing this exercise because here I'm assuming that the axial effects are not present. So when there is only flexural effects, then the force in the beam is actually given by 4x1 vector. If there are axial effects, then we have to consider axial degrees of freedom that we are going to discuss next. And so it depends on the problem. Okay, so whenever the problem is given, so think about it, whether you have to consider axial effects or not. And this is the beam element stiffness with the axial degrees of freedom. So when we talked about the axial degrees of freedom, so we just actually, what we did is we just added the stiffness coefficients for the bar member into the beam member. That's how we incorporate the axial effects. And now the degrees of freedom are, at the I end, they are ui, vi, theta I, and at the j end, they are uj, vj, theta j. And for the beam, we always assemble in this fashion: ui, vi, theta I, uj, vj, theta j. Okay, this is the order of assembly, and then this is the stiffness matrix. And the forces are pxi, pyi, mi, pxj, pyj, mj. Now you can see that the force vector is a 6x1 vector. And the displacement vector is also a 6x1 vector. So the difference between the this case and the case where there's no axial degrees of freedom is that this kind of element is useful when there are some axial loading on the beam, or there's some axial like a traction is applied, or any kind of axial effects is going on. Okay, so you have to consider this kind of beam element with axial degrees of freedom. So here bar indicates it's written in the local system. The reason is because this can be used to get the stiffness matrix for the frame element. So that's the reason I put the bar here, just to indicate it's in the local system. But for the beam, we always work in the local system. So we don't have to worry about the bar for the beams, but it is important for the frames. Again, for the beam, if we want to consider the member effects and consider the equilibrium, we have to make sure that we have to consider the member effects, means the fixed end forces due to the whatever the loads acting on the member, and then you have to get those fixed end forces and add them to the forces due to displacements. So total forces are forces due to displacements plus the fixed end forces due to whatever the member loads are. And again, you can see that in this case, I am also including the axial component of the fixed end forces. Okay, so they might not be non-zero. For example, if there is axial traction acting on the beam member, so you should consider these 6x1 vector in this case. And this is how we will calculate the beam element member forces if the axial effects are also present. So it depends on if there is axial effects or not. And next, actually, after the beam element, we talked about the 2D frame elements. And for the 2D frame elements, we can look at element in two different ways. Either we can look into the in the local coordinate system, or we can look at the element in the global coordinate system. But what is needed for the solution process is the system in the global coordinate system. So this is what is needed. Okay, so you need to know what is k and p0 for an element, and these are the numbers that you need to assemble into the global system, because global system is always solved in the global coordinate system. But the reason why we want to look into this element in the local coordinate system is that we can get k and p0 from k bar and p0 bar actually by transformation, and that was the idea that we used in our class. And in this local coordinate system, this beam is this frame element is actually equal to the beam element. So this is exactly the same as the last slide. So there's no difference. So I just take this element and just rotated it. Nothing is changing. So this is exactly the same. So p bar, k bar, d bar, po bar are actually these numbers here. So then nothing changes here. Okay. But the idea was how can we get this equation from the local coordinate system, and then we use the idea of transformation. And using the idea of transformation, we are able to transform from local to global or global to local. So we can go from both ways. And for the 2D frames, we said that the transformation matrix is a 6x6 matrix, and this was like just this is like you can think like a CS minus SC, and this third coefficient is 1, and this block is repeated here. Okay, so again CNS depends on the orientation angle, so make sure that you calculate the orientation angle correctly. So once you have the orientation angle, you can get this transformation matrix, and with this transformation matrix we can actually transform between any of the displacement and forces. So we can so here P bar is local, P is global. So this is, we can express local quantities in terms of global quantities, or we can do the inverse process. So we can express the global in terms of local. But another important property of this T is this is the orthogonal matrix. So actually the inverse of this matrix is just transpose. And that's the reason I just put the transpose here, because technically I should put an inverse, but inverse is equal to transpose. So I just use this property of this to write this. And this is the same equation is valid for displacement. So exactly the same format. And finally, we can express K in terms of K bar. So we can take this stiffness matrix. So this is the stiffness matrix written in the local coordinate system, and bring it to the global coordinate system, and that is K, using this transformation here, T transpose K bar T. And this is the thing, this is also the way you are actually implementing in your codes, also in your finite element, or in your like a finite element matrix code, like using MATLAB. And finally, K. So for like solving problems like by hand, actually I gave you the explicit expression of K. So I did the algebra, and this is the K. This is what the K looks like. Now you can see that it has all the entries with C square, S square, CS, and so on and so forth. But actually, this is still a symmetric matrix. So technically, you just need like half of it. If you're trying to calculate the entire matrix, don't do that. You just need the half of the matrix, and typically it depends on how you're solving it. Sometimes you don't need all the coefficients. Okay, you can just use selective entries from this matrix. But you can use this matrix directly for solving your problems in the exam, or even for the homework. And finally, we can also express the fixed end forces in the global system. So we already, the fixed end forces in the local system is given to you. So this is what I will provide. So local system is provided. The global coordinate system you have to calculate. And we can calculate this by using this transformation here. So it's the PO is the fixed end forces in the global system. This is just T transpose PO bar. Okay, so this is the algebra. And if you do the algebra correctly, we should be able to find the fixed end forces in the global system. So this is the algebraic process of doing it, but we can also take the components of these members, P bar and P bar OX and P bar OY in the global X and Y direction, and do the algebra directly. That's the way I also did in one of the lecture slides. So it depends which way you prefer. So this is the algebraic way of doing it, or you can just do it by taking the components of these forces. But both of the methods should give you the same answer. And once you have the fixed end forces, we can write the equilibrium for like a single frame member. One other important thing I want to point out is when you're calculating the member forces after solving the problem, the member forces for a frame element should always be presented in the local system. So member forces for a frame element means you are doing this calculation. Okay, so they should always be presented in the local system. They should not be presented in the global system. And finally, the final thing I did is actually I did a lot of problems where I didn't actually build the individual element stiffness matrix. So what I did is I directly used the idea of like the physics of stiffness coefficient. So what is the meaning of physics here? So for example, we know that Kij means the force at the ith degree of freedom due to unit displacement at j degree of freedom, while all the other degrees of freedom are fixed. What does it mean? That if we want to find, let's say, first column of a stiffness matrix, we have to take the first degree of freedom, move it by 1 unit, while all the other degrees of freedom are fixed, and calculate the force in that configuration. And that all the forces will give us the stiffness coefficient in the first column, and so on and so forth. So we can choose any column from a stiffness matrix and do the same exercise. And this is a more like a physics-based method to build the stiffness matrix. So it also gives you like some intuitive ideas, like how the forces are flowing within the structure. So this is just a fun method to work with. And to work with this method, actually, I gave you these stiffness coefficients for beam and frames that can be used directly, so we don't have to build like any stiffness matrix. So I give you these these 4 slides. So these are important slides to remember. So in the first case, what is happening? There's a beam element. The I node, there's a displacement, a unit displacement in this VI degree of freedom, and these are the forces. In one of the earlier slides, in one of the lectures, there was a typo here, so this negative was missing. So I have put the negative sign here also in this 4th here. So this was one of the typo that I have fixed. But just remember that you can use these numbers directly in your problems, okay? And so this is the second case, is where the rotation at I degree of freedom is 1. So this you can think are for the beams, but I can take those beams and rotate it by 90 degrees, and I'll get the column. So you can think that these are the displacement degrees of freedom for a column. So these are the same coefficients, but this is just a different way of looking at the numbers. And I use these numbers directly, and I have used these numbers for solving a lot of problems, especially in the last few lectures. And so this is like another way of solving the problem using stiffness method, where you directly build the KFF or whatever the entries are needed, just by displacing the degree of freedom and calculating the forces that are needed in that configuration. And then there are 2 more cases. This is at the displacements at the J degree of freedom. So there is a rotation at J, and this is like this is a rotation at J, and this is like a vertical displacement at J, and these are the corresponding forces. And again, I took this configuration and rotated by 90 degrees to get the column, and the numbers are exactly the same. Now the beam looks like a column. And if I use these numbers, I don't have to worry about transformation and everything. I can just use these numbers directly to build the stiffness coefficients. So they come in pretty handy if you are able to use it correctly and carefully. I encourage you to use this method. And so both the method should give you the same answer. Either you build the element stiffness matrix for each individual element and assemble them together into a global system, or you assemble the stiffness coefficients directly by taking a displacement degree of freedom and moving it by 1 unit and finding the stiffness coefficients directly. So both these methods should give you the same answer. And so there are actually 2 ways of doing things, but they are connected to each other. And I hope that you are able to use both of them. So whichever, or you can just use a method that you like more, or you have practiced more. So it's up to you. It's your choice. I like the direct method where you displace a degree of freedom and build the stiffness matrix directly. The reason is, for me, it's a very intuitive approach. And I also kind of because I do research in this area. So for me, these numbers I always remember these numbers, like 12 by L cube and things like that. So I can easily build a stiffness matrices just by looking at the structure. But it comes by practice. So if you plan to become a structural engineer, this is definitely the method of choice, because it also gives you an intuition. So if you go in the field and if you see that most of the top structural engineers, this is the way they actually think about the method. So they can think about in their head, okay, how the structure is deforming and what are the stiffness coefficients and how the forces are flowing. So this gives you a very good intuitive understanding of the method. So I would encourage you to use both of them and just see whichever you can understand in a better way, and just use whichever method you like. And these are the more fundamental elements that we looked at. And actually, after that, we looked at some different ideas. Some of the important ideas that we looked at, one was the idea of the internal hinges. And as I said, that internal hinges are used to break the discontinuity, or to think about, to break the continuity of the rotations. So whenever there is a hinge, it means that you can rotate the sides of that member independently. So if there is a hinge, for example, in this beam here, so it means that there are two rotation degrees of freedom on each side of the hinge. So there's a rotation, the rotation at right of the hinge is independent of the rotation at the left of the hinge. So they can, both sides can rotate independently. That is the meaning of the hinge. So so hinge is easy to consider. You have to just add an additional degree of freedom and consider it as a separate degree of freedom, and then you're good. So a hinge, just so whenever there's a hinge, make sure to increase the degrees of freedom in the structure. And then we also considered the idea of unbraced and braced frames, and we talked about that. Okay, bracing helps to actually reduce the lateral displacements in a frame. For example, this is a portal frame that is not braced, and there's a portal frame with one bracing. So here the idea of bracing is nothing but a truss member. Okay, so brace member is a truss member. So brace member can only carry axial forces. It cannot carry any moments. And for this reason, we never apply, let's say, a uniformly distributed load on the brace member. We never do that. Okay. Because if we try to apply uniformly distributed load, then it's no longer a brace member, it's actually a beam member. And by definition, a brace member, we want to make sure that the brace is only carrying axial forces. And that's the reason the brace member is connected to a frame by this hinges here. So the hinge actually, because of the hinges, the movements cannot be transferred from these beam or columns to this brace. So brace is only under axial deformation. So a brace member will only have like 4 degrees of freedom because it's like a 2D truss element. So you can directly consider the brace member in the analysis of any frame that is given to you, and it should be a straightforward way of doing it. You just have to think that brace member is just a truss member and just do the analysis. And then we also considered the idea of support settlements. Support settlements is like whenever you have prescribed displacements, those are actually support settlements. So support settlements typically happen because of many reasons. For example, you can have some soil consolidation going on. So I'm pretty sure that you have taken a class in geomechanics, and they talk about consolidation of like soils. So the whole foundation system actually sinks sometimes, and it sinks unevenly. So you can think that some portion of the structure is actually sinking, and then those you can think as support settlements. And finally, we also talked about the concept of introducing springs in various ways. And sometimes the use of springs is to actually consider elastic foundations. Elastic foundation means that you are trying to model the stiffness of the soil system itself. Okay. So for example, you can think like this is a beam, and this beam is actually sitting on some kind of a foundation, and this you can think that this stiffness coefficients Ks1 and Ks2 represents the stiffness of the foundation itself. And typically these numbers you learn from geotechnical engineering, what these numbers should be. For our class, I just give you some numbers to work with them, but actually they have some meaning. So those numbers can be calculated based on some geotechnical engineering concept. And I hope that you might have learned something about these things in your other classes. But I think the idea is more important here. So we can use springs in various ways, and we can mix. So in a given structure, you can have springs also, truss elements also, and beam members also. So you can see that a structural system can have all these members, and we should be still able to solve that system by carefully using the correct stiffness coefficients for all these members. Hopefully, this course give you like enough background or enough information that that you will need for your like future practice. And definitely this will be a good class in case you go for a graduate school and you want to learn further about these concepts. And I would like to end this class by telling you that this is actually, you can think this is the very first basic class in this structural analysis. Okay, there are many concepts that that can be learned actually, and I have not covered them because we don't have enough time to learn everything in one class. Typically you will need like 2 to 3 classes to learn like different concepts. And some of the direct extension of this method is actually 3D frames. We could have actually directly used the same ideas that we have considered in our class to build like 3D frames. And actually in the past years I have included that topic in the class, but this year I think because of the time restriction, and I was not able to reach to that point. But it turns out that the 3D frame is not very difficult. So we can actually, what we can do is the idea remains the same. For example, let me go back here. For the 3D beam element, what's going to happen, that we will see that this beam element, instead of a 6 degree of freedom, the beam has actually 12 degrees of freedom. And then the thing is, those kind of problems cannot be solved by hand. So the only way to solve those big problems are using MATLAB. But it can be easily done. So we can take this system and include more degrees of freedom. So what happens that if there is a beam element in space, every node has 6 degrees of freedom. Okay, so you can think that there's 6 degrees of freedom here and 6 degrees of freedom here. So a single element will have 12 degrees of freedom. So the stiffness matrix for a beam element will be 12 by 12. Again, you will have the similar way, the fixed end forces will be a 12 by 1 vector. And again, we can write this in the local coordinate system, and we can write in the global coordinate system for a frame member also, like a 3D frame member also. And then finally, what we can do is we can use the same idea of transformation to go from local to global. In that case, what's going to happen? The transformation matrix will be actually 12 by 12 instead of 6 by 6. So you can see that the algebra is cumbersome, but we are not doing by hand in that case. We are always doing by all the algebra by MATLAB. But it can be done in a very straightforward way. And that is one of the reasons this method is a very powerful method. So we can directly like analyze 3-dimensional spatial frames with this method. And this is a very straightforward way of incorporating 3-dimensional members, like frame members, in our method. So this was one of the direct extension. And actually, other than that, there are many other extensions actually. But this is only the extension in the linear case. And once you go into the nonlinear regime, this thing is endless. You can spend your whole life learning about nonlinear structures. And there are so many things that can be learned and that can be done. And but this idea is very powerful. This is not only valid for beams and frames and trusses. The idea of stiffness method is also valid for 3-dimensional structures. For example, if you want to analyze like a spatial dome, or like that is like made up of shell elements, like you can think about, or something that is made up of solid elements, the same idea applies. Even the same programming concept applies. So the only challenge there is how to build a stiffness matrix. So for example, if I go back here, this is a stiffness matrix for let's say 2-dimensional frame element. What happens if I try to build a stiffness matrix of a, let's say, 2-dimensional plate element, or 3-dimensional plate element, or a shell element, or a solid element? It turns out that there's a whole course dedicated to these kind of things, and you learn typically these things in a finite element course. So there's a rigorous finite element course which teaches you how to build stiffness matrices or different kind of elements. And these courses are from like very basic courses to the very research oriented courses. So there's so many things that you can learn in this area, and this is, you can think this is just the very first introductory course in this area. And as for myself, actually our group do a lot of research in these topics. So our expertise is actually in nonlinear structures and solids, and how to optimize them and how to do different things on them. So that's the reason I know a lot about this topic. So you're always welcome to stop by if you want to know more about anything. Make sure to feel free to ask question, and even after you graduate and move away from Notre Dame, you can always contact me. And if you want to know something about structures, I will be always available to help you out. At least I'll try to tell you what I know about these things. And after that, I want to talk a little bit about the final exam. The final exam is actually on 7th of May. I think the day is Thursday, and the time is 10:30 in the morning to 12:30 in the afternoon. And so it's a take-home exam, because I'm hoping everyone is safe at their home. So you can take the exam in the find a good place in your house, so where there's no disturbance, and take the exam there. And this is going to be an open book and open notes exam. And the content of the exam will be this is going to be a comprehensive exam. So the problems will try to explore all the concepts, okay? Because you can see that these concepts are all very connected, so we cannot disconnect. So for example, if we have a problem like base frame, so in this case actually we are using both the frame members and the brace member in the same problem, okay? Or like a truss member in the same problem. Or I could have put a spring here also. So you can see that in one problem I have all kind of elements. And so all kind of you need to understand all the topics carefully, okay? So make sure that you understand everything that is covered in the class, because all the problems, you can think that I can put everything, a problem can have different kind of elements, and you should be able to use them in the correct way. So I would say that the best way to study for the exam is actually go through all the lecture slides, and make sure you understand all the example problems that were covered, and also make sure that you go through all the homework solutions and your homework, like your own solutions and my posted solutions, that to make sure that you understand all the homework problems and how they were done. And if you have made some mistakes, make sure not to repeat the same mistake in the exam. So everything will be covered. Everything that is covered in the lectures will be included in the exam. And I'm planning to have, let's say, around 5 problems in the final exam, but I have not yet decided. There might be 6 problems, or there might be 4 problems, depending on how difficult the problems are or how long the problems are. And but the focus will be on with the primary focus on beam and 2D frames, okay? And but there will be I'm still deciding how many problems or how to break up the problems, but I'm thinking maybe 1 to 2 problem on trusses, and let's say 3 to 4 problems on beams and frames, okay? So that should give you an idea the format of the exam. But make sure that you understand everything and you understand all the homeworks, and I think you should be able to work through the exam in an easy way. It should not be a difficult issue. And but feel free to ask me if you have any questions or any concerns, and I will try to set up one more office hour, like a help session, and I will announce that time in few days, okay? So you can always but in the meantime, feel free to ask me if you have any questions or anything you want to know more about the course, or anything else actually related to structures. Then I will be very happy to help you out. And with that, I would like to end this session, and I hope that everyone is having a great time. Bye-bye then.